response today. So over to Professor Nesterenko.
Thank you very much for this nice introduction. Thank you very much to organizers for the invitation to give a lecture about transcendental number and this beautiful conference. Thanks. So the title of my lecture is Algebraic Independence and Modular Forms. I start from short introduction to E and G functions. Let K be finite extension of the field of rational numbers, degree nu. Zk is a ring of integers of the field K. For any A in this field, I'll use this notation for the maximum of absolute values of all numbers conjugate to A. In 1929, Siegel introduced two classes of functions, E and G functions. They have some common in definition, so I start with prerequisites and after that the definition. Let be A0 and A1, A2 numbers from the field K, and at first there exists a constant such that all conjugates of n's coefficient are less or equal to some constant to the power n plus 1. Power depends on the number. And second, this is condition for denominators of these numbers. There exists a sequence D of natural numbers such that D is a common denominator for all elements of this sequence from 0 to n, and growth of this denominator is bounded by geometrical. It's the same as absolute values of conjugates. So these are conditions for this sequence. And now definition, E function is a sum of such series. Due to first condition, E function is entire function. And at second, definition of G function, almost the same, but there are no factorial in denominator. G functions have finite radix of convergence. So E function is entire function, and this G function have finite cycle of definition. Well, I start maybe from the first result about algebraic independence of numbers. These are values of the exponential function. If alpha 1, alpha m are algebraic numbers that are linearly independent over rationals, then values of the exponential functions are algebraically independent over the field of rational numbers. They are not connected to any polynomial with rational coefficients. So Siegel proposed E function as a possible candidates for generalization of Lindemann-Weierstrass theorem. Bigger class of functions with such statement. The typical example of E functions are hypergeometric functions with rational parameters. So A and B are rational numbers. Of course, B is distinct from 0, -1, -2. This product is Pochhammer symbol, product of all numbers shifted by 1, starting from alpha and n factors. So if A is equal to 0 or -1 and so on, so this function is a polynomial with rational coefficient, and it's not very interesting example. So hypergeometric functions with rational parameters. Mainly these are E functions. So main result about these E functions was proved in 1955 by Shidlovsky. This is a general theorem that reduces the problem of number theory, transcendental number theory, to a functional problem. Are there any algebraic relation among these E functions over the field of rational functions? I would like to say that Ziegel proved his result, his theorem about transcendence of values for functions that are solutions of the differential equations of the second kind. This is a general theorem. Suppose that E functions f1, fm form a solution of the system of linear differential equation with coefficients rational functions, and alpha be any algebraic number not equal to 0 or pole of one of the functions Q capital. So this is not singular point of the system. Then the values of these functions are algebraically independent over rationals if and only if the functions are algebraically independent over field of rational functions. So this is a complete reduction of this problem in transcendence number theory to the functional problem. If we have some set of function, for example, hypergeometric function, what are conditions on parameters A and B such that functions are algebraically independent? For example, this is a typical problem, and Shidlovsky's school had many results in this direction. This is not the same situation, completely the same situation as this exponential function, because it's easier to prove algebraic independence than a linear one. For exponential function, these are almost the same problems, full difficulties. So this theorem was proved in 2004 by Fritz Beckers. Let f1, fm be a solution vector of a homogeneous system of first-order differential equations over the field of rational functions, and suppose that the functions are E functions linear independent over the field of rational functions. So we assume that these functions are linear independent. Let alpha be any algebraic number not equal to 0 or singularities of the system, then these values are linearly independent over the field of algebraic numbers. So these two theorems, in my opinion, these two theorems give a complete solution problems connected to E functions. Unfortunately, situation with G functions is much more difficult because there is only finite, only bounded set of definition of the function, and there are no factorials in denominators, and this makes some difficulties in estimates of functions. So. But maybe some examples at first. Any algebraic function is a G function. For example, this function, it is connected to Fermat's theorem. Question is it possible to find rational number Z such that the value of G function is, especially this G function, is rational? This is Fermat. Next is a Gaussian hypergeometric function. So A, B, C are rationals. And question is about rational parameters when the values are transcendental, for example. This is open problem. Next example are polylogarithms. Values at the point 1 of these functions are connected to zeta odd zeta values. It's well known that zeta 3 is irrational, but nothing about transcendence and nothing about zeta 5, 7, and so on. Some words about general results. Ziegel in 1929 predicted that some reduction of factorials should be performed for G functions, and this property should be useful for studying the values of these functions. In exact form, this property was formulated in 1974 by Galochkin, who proved it in some special cases. In general case, this property was proved in 1985 by Grigory Chudnovsky. He said about this as G property. So G functions should satisfy some system of linear differential equations with rational coefficients. Now this is a G property, what definition of this property. T is a common denominator of all coefficients. This is a polynomial with integer coefficients. So in fact, rational functions should have rational coefficients. Then if we compute derivative of this vector as derivative multiplied by t to the s and divided by s factorial, we derive some matrix with polynomial coefficients, and condition is on denominator on the common denominators of all elements from all matrices. So we say that this system of differential equations has G property if this common denominator is geometrical growth for some constant. So we have factorial in denominator. Nevertheless, coefficients have denominators for coefficients have geometrical growth. So this is a general result about linear independence of G functions. This is best up to date. Let F be solution vector of a first order system of linear differential equations with the G property. Suppose that the G function with coefficients in the field of rationals. Suppose also that these functions are linearly independent. So these are standard properties for E functions. They are linearly independent. Then there exists a constant such that these values at rational point A over B are linearly independent over rational numbers whenever A and B are integer and B is essentially larger than A. Only with this condition, it's possible to prove anything about linear independence. We have no such condition in the case of E functions. And a general result about polynomials. This is theorem proved by Chudnovsky in 1985. Let F be G functions satisfying a system of the first order linear homogeneous differential equations, and be algebraically independent over the field of rational functions. Then for any t larger than 1, there exists a constant C0 such that for an arbitrary algebraic number eta, distant from 0, of degree at most t, the numbers f1, the values of g function at the point eta are not related by an algebraic relation of degree t over the field generated by this eta, provided that eta is rather small in comparison with height of this number eta. So we have some parameter t. It bounds from above the degree of this algebraic number eta, and numbers are not related by algebraic relation of degree t. So some bound for degree of the point gives some bound for algebraic relation. In this condition, and with this condition on point, there are no algebraic relation. So we have a very limited set of possibilities for degrees of polynomials connecting these points, values, and so on. If we compare this with Galchkin's theorem, so this is a case of t equals 1. In Galchkin's theorem, there is a linear situation, and eta is a over b rational number. Height is a maximum of a and b. Since point is very small, then this maximum should be equals b, and condition is this condition can be written in this form in Galchkin case, and this is formulation the same condition in Chudnovsky notations. So this is almost the same for t equals 1. So results, both type results are very poor in linear and polynomial case. Nevertheless, there are some cases when it's possible to prove something much better than for G functions than in this situation. At first, this is connected to Ramanujan functions. Ramanujan series were introduced in 1916 by Ramanujan, and these are definitions, P, Q, R, 3 functions. Sigma is a sum of case powers of divisors of the number, power of Z. And as Ramanujan proved, these 3 functions satisfy the system of algebraic differential equations, not linear, algebraic. And these functions are G functions, of course, because coefficients are integers and they have polynomial growth. This is not geometrical. Very slow as polynomial. But the system of differential equations is polynomial. This is more difficult than in linear case, usually. Now I would like to define some field K. This is algebraic closure of the field generated by tau. Q is exponential function e to power 2 pi I tau. It is, and with these notations, Ramanujan functions will be defined in upper half plane. And this field is closed with respect of differentiation. So D is a differential operator where, because all functions in this Q are power series in Q, so we can apply this first form of the differentiation, and for the number tau, another one. But this is the same differential operator, in fact. So algebraic closure of the field generated by Ramanujan functions Q and tau. In 1969, Mahler proved that the transcendence degree of this field over complex number equals to 5. And this is a natural area for results about modular function and many other functions, and I want to shortly explain the situation. So it's not difficult to conclude that this field K contains the modular functions lambda, J, Eisenstein series, because connection is very simple. E tau should be, oh, I'm sorry. No, it's okay, I think. E2, this is Eisenstein series. E2, E4, and E6. So PQR, this is Fourier expansions of Eisenstein functions. Moreover, so these functions are defined in upper half, complex upper half plane. Moreover, for any rational numbers a and b, this theta function is a function in two variables, z and tau. And if you put here instead of z this combination with rational a and b, this will be function from the field K. Another example, elliptic function of Weierstrass with algebraic invariance, where we put instead of z this combination will be element of the field K. So the variety of functions, elliptic functions, modular, hypergeometric, involved in this story connected to Ramanujan functions, and connected by this function are connected by different identities, allowed to receive many results about transcendence and algebraic independence of values of these functions. So let's give some examples. This theorem was proved by Chudnovsky in 1976. Let P be Weierstrass elliptic function with algebraic invariants G2 and G3, and delta is a discriminant, and let omega be a non-zero period of this Weierstrass function and eta corresponding quasi-period. Then these two numbers over omega over pi and eta over pi are algebraically independent. In particular, numbers pi and gamma 1 over 4, these are for special values of this invariance. In numbers pi and gamma 1 over 4 and pi gamma 1 over 3, algebraically independent over rationals. So some corollary of this Chudnovsky theorem, there is a link between these parameters of P function Weierstrass and Eisenstein functions. For any complex number tau with upper half plane, at least two of numbers are algebraically independent over the field of rationals. So there are two numbers in Chudnovsky theorem and two numbers in values of Eisenstein series. This because of the some connections between these two sets of numbers. And in 1996 was proved more general result. For any complex tau from upper half plane, there are at least three of numbers that are algebraically independent over rational numbers. So there are four numbers. We can take tau by proper way. We can take I, and in this case, this value is 0. And rest, these three numbers, will be algebraically independent. And this is the same for the case when this exponent can be algebraic number, and then these three values of Eisenstein series will be algebraically independent. So some examples, precise examples. If we take tau equals to I, we derive algebraic independence on these three numbers, pi, e to the pi, and gamma value of 1/4. These three numbers are algebraically independent. In particular, pi and e to the pi are algebraically independent, and this means that for any polynomial with integer coefficients distinct from 0, the value at the point pi and e to the pi is transcendental. For example, sum of these numbers, product, some fractions, and so on. And some general corollary of this theorem was proved by Daniel Bertrand. Let f tau be a non-constant meromorphic modular form defined over rationals for all alpha complex numbers from upper half plane distinct from poles of the function f, such that this exponent is algebraic number. The numbers f alpha, first derivative, and second derivative are algebraically independent over the field of rationals. So there is only one condition, that this exponential function should be algebraic. The functions, Ramanujan functions, they form some transcendence basis of this field K. In fact, there are different bases. For example, we can take bases consisting from logarithmic derivatives of theta constants. So theta function, this is function in two variables, z and tau. And if we substitute some combination of tau instead of z, we derive three basic theta constants. They are functions, but the official title is these are theta constants. Theta 2, this is expansion in power series. Theta 3, another one, and theta 4. You see, all coefficients are units or minus units. Q here is e to the power I pi tau. Modular invariant, lambda tau, this is a fraction of fourth powers and theta 2 and theta 3. H, this is the upper half plane for any tau from this set, absolute value of Q is less than 1, and differential operators is pi I in denominator, because of this is I pi tau, and in the variable Q, this is exactly the same as in case of Eisenstein functions. Now logarithmic derivatives. So this is logarithmic derivative of theta 2. I denoted psi 2, the same psi 3 and psi 4. And it's possible to expand these functions in Fourier series, and we have excellent coefficients. They are integer numbers. In these two cases, chi is Dirichlet character model 2, so it equals 0 or 1, and summation is on divisors of k. So these are integer numbers, and in this case, linear growth, and so they grow not very fast, even in comparison with Ramanujan series. There are many identities connecting all theta function, modular function with this psi2, psi3, and psi4 logarithmic derivatives. For example, fourth powers of theta constant can be expressed in logarithmic derivatives by this way. And in 1881, Alphand proved that these three functions are connected by algebraic differential equations. There is a singularity at 0 because delta is q multiplied by d over dq. So in q equals 0, we have singularity here. And this symmetry, in fact, this is a function, differential equations, they're analogous, analogous to Ramanujan differential equations. But in this case, the system is symmetric. And all derivatives of theta 2, 3, 4, and for lambda can be expressed in terms of logarithmic derivatives. And it is easier to work with these functions because of the symmetry, and coefficients growth is slowly, and so on. The following result is not new. There are two of its various proofs. Both of them are based on different modifications of Gelfond method. The first one was proposed by Chudnovsky, and the second one by Ivan Re. Further, we will describe the third approach, realizing an original method of Ziegel-Shidlovsky. The statement is, so these functions, Gaussian hypergeometric functions, they are G functions, and statement is that for any algebraic number from unit cycle, these two numbers are algebraically independent. So you see, this is G function, like in Ramanujan functions case. This is another set of G function where we can prove algebraic independence. We have no general theorems, but in some special cases, we can prove algebraic independence of numbers, of values of G functions. This is a sketch of Chudnovsky proof, very short. We take this elliptic curve, these three variables, x, y, z, and it is parameterized by Jacobian elliptic functions, Sn, Cn, Dn. U is a variable. They have period for k and corresponding quasi-period for e, where k and e can be expressed as integrals, and in terms of hypergeometric functions. So this is 1/2, 1/2, 1, and 3 over 2, 1/2, 2 psi. This is not the same as -1 over 2. But there is a very, very easy reduction of this case to the case with 1/2 these parameters. So this is identity. And due to Chudnovsky's theorem about elliptic functions, k over pi, k over pi and e over pi should be algebraically independent. And this gives algebraic independence for values of Gaussian, this special case of Gaussian functions. So this is Chudnovsky's theorem about period and quasi-period. He used Guilfont's method for elliptic functions. And as a consequence, we have algebraic independence of values of these two. This is theorem again. And this is a short explanation of reduction. So these three functions with parameters 1/2 and derivative here, and second set with parameters 1/2 and 3/2. These two sets are linearly dependent over the field of rational, over the field of this finite extension of rational numbers. We assume that psi is algebraic number. And it's easy to express this this number by this one for these linear equations, and finally derive the algebraic independence of these two values of different hypergeometric functions. Now I want to explain the Ziegler-Shidlovsky approach in this connection. So these are functions f1 and f2. This a and b are integers. This the precise expression in binomial coefficients. They are bounded by 16 to the power n. So in fact, coefficients are not larger than 1. And this f1 and f2 are G functions. We can parameterize of these two functions by theta constants. For example, if we put in this function lambda function instead of argument, we derive this 4 times psi 2 over 3 2 squared. And in this case, this is the same lambda function, we derive theta 3 squared. The proof is based on the system of differential equations for psi, for logarithmic derivatives, and the same differential equations for this function f1, f2. F1, f2. So to prove these identities, we can compute derivatives of these two functions, and this is a second set. So left and right functions. And after that, by induction, we can prove that all coefficients in this left and right functions are the same. And for second case, coefficients coincides too. So these are easy calculation of derivatives and comparison of coefficients. Next, there is since lambda and psi, lambda is a modular function, psi is quasi-modular function, but in this case, it's possible to write so-called modular polynomials. These are polynomials connected, for example, lambda r tau and lambda on tau. So r is any odd is convenient in this situation. So any odd r and lambda tau. For these two, there is a functional connection of these two functions. And it's possible to estimate degree of this polynomial and height. Bounds are written here only for degree, but it's possible to write for height, second logarithm will be here. And this means that if lambda of tau is algebraic number, then lambda of r tau is algebraic too. The same as for other functions. And we have sequence of points, algebraic points, where this hypergeometric function have algebraic values. So if at the point psi, lambda of psi is algebraic, and value of the hypergeometric functions are algebraically dependent. So by this way, we can construct infinite sequence of points where argument lambda r tau is algebraic, and values at these points are algebraically connected. You see, problem is that algebraic point can be any point in a unit cycle, even rather far from zero. But for the case of G functions, all general results were proved for points that are very close to zero. But if you have such infinite sequence, it's possible to compute infinite sequence of points with this property. And it tends to zero, in fact. And we can choose this number R and apply this technique of Ziegel-Shidlovsky to points that have some good properties. So assume that psi is algebraic, and this is that I told you. So we defined this zeta for in terms of psi, and these are values of functions. They are expressed in terms of logarithmic derivatives and theta constants. So if okay, this is these are values of hypergeometric points. Yes, you see this field. If we assume that at the point psi values are algebraically dependent, then in this case the field K has transcendence degree 1, and these numbers have degree 1 over the field K. This means that the numbers are algebraically dependent. So this translation of properties to the point lambda r eta, rz. So these are some bounds for degree, for height of this number in terms of r, the value of this point eta, and this is the Chudnovsky theorem again. This is general again, and I want to show how this property is correct if we take R sufficiently large. Of course, it's impossible to use this theorem directly because these constants are not computed effectively in Chudnovsky proofs. But the method is effective, so it's in principle it's possible to calculate all these constants, all these dependencies, and this if R is large and connected by some way with this height, for example, and degree, then this condition is satisfied. And we have contradiction with this condition on T. So we can take T depending on R, and finally this will be correct. And we find the algebraic relation But Chernovsky theorem says that it's impossible. This is a finite contradiction. So I should stop. I should stop now. Thank you very much for your attention. That's all. Thank you.
Thank you, Professor Nesterenko, for a very interesting lecture. And I'm sure people have questions. And people who have questions, can you please unmute yourself and ask the question? I see Professor Waldschmidt in the audience.
Yes, I just want to say congratulations, because it's very nice talk, very general, and also you get a new method at the end, which is very interesting. So thank you, Yuri, for your lecture.
Thank you, Michelle. Thank you.
Very nice to hear. I had a very simple kind of question. I don't know whether it makes sense. The values of gamma, let's say at 1/5 or something like that, they don't arise in this manner, right? In terms of Eisenstein values and all. So is there any result about algebraic independence of gamma values at 1/5 and things like that?
Yes, I see. I see. Even gamma value at the 1/5, irrationality of this number is not known.
Okay.
So this problem is connected to abelian varieties and not one-dimensional integrals, but with more dimensional. So this is very interesting area, and but it's not easy. So this is a main problem.
Okay, thank you.
I want to mention one more problem. So this business with G functions and with denominators, it is connected to transcendence of zeta values. For example, classical relations of zeta values to these functions, to modular functions. And in principle, it's possible to try to prove transcendence of zeta 3, for example. This, of course, this is a difficult problem, but it's very interesting.
Thank you, thank you. So are there other questions?
Professor, may I ask one question?
Please go ahead.
Yeah. First, I'd like to thank Professor Nesterenko for a wonderful talk.
Thank you.
Yeah. So you have given a result related to 2F1. So is it possible to extend your result like for 3F2 kind of hypergeometric series? Like,
I don't know.
Okay.
No, but maybe we should use abelian functions or something like this.
Okay, I see. Actually, why I'm thinking like generally PFQ, when P is like Q plus 1,
Yeah.
they have same kind of like, it may be complicated, of course. Yeah.
Yeah.
So that's why I was thinking that whether is it possible to extend your result for like a P plus 1 FP?
Mm-hmm. Yes, but so even in the case of 2.1, so this is a Gaussian function, we have such results only for very special choice of parameters. Even in this case, there are many difficulties.
Okay, I see. I see.
You think about algebraic independence. So.
Okay, I see. So one more question, Professor. Now, since 2F1 are also coming from a solution of a differential equation, second order differential equation. So I was just wondering that whether these kind of results also holds for like Bessel function of the first kind.
You see, Bessel function, this is E function.
Okay, I see.
Of course, this is not completely E functions. There are some connection to E functions, but there is some factor that connect this Bessel function to E function. In this case, results were proved by Ziegel. Of course, this is not completely for Bessel function, but some functions that is connected very close to it.
Okay, okay. Thank you,
It's not
Professor. Yeah.
29.
Okay.
So are there other questions? I see one hand raised. Rajendra Lekhwar, do you have any question?
Yes, sir. Good afternoon, sir. This is Rajendra Lekhwar. Professor Nesterenko, I wanted to ask you one thing. This is not related to your talk, but generally related to this one, higher arithmetic, I mean number theory.
Yeah.
So I just wanted to know what exactly one should study to understand Fermat's last theorem, this one, Andrew Wiles' version of Fermat's last theorem. What exactly to study, which all the things are to be prepared, so that like how much modular theory, how much elliptical functions, and so some idea, please. I mean, I don't know whether I should ask you this, but since it is pertaining to number theory, which is why I just collected my guts to ask you these things. If at all you could help me out, please. What exactly to study to understand the matter completely, or at least to make it understandable.
I'm very sorry, but I believe now we have no time to discuss
Yes.
this
Yes, I think,
technical question. Please write me a letter, and we can write discuss this by letters, by mail.
Sure, if you could. Sure,
Yeah.
Professor. If you could put your
Yes,
mail
yes.
ID, please.
We will share it. We'll share it with you, and later.
All right, sir.
Okay.
Thanks
so
a lot.
Thank
Sir.
you.
Thank you very much.
Professor Nesterenko, for being an excellent lecture and also answering questions. So let's thank him once again for this talk.
Yes.
Thank you.
And over to the organizers.
Thank you, Professor Nesterenko and Professor Suri. We will have a contributory session, track 1 and track 2 from 13:45. 14.
Not 13.
Contributory session, track 1 and track 2. Discrete mathematics papers.
It is 2:40 now, so
Yeah,
not 13:45.
2:45. Starts at 2:45.
14:45. Okay, thank you.